All right, we're going to look at a couple examples of the exponential functions problems on your Snickers worksheet. So hopefully that'll get you some help, the help that you need on your Snickers problem. All right, two examples. Let's first look at this one. We've already seen this one as a warm-up, but we'll look at it in a little more depth here. Selena's starting salary, annual salary at her new job is $32,000. Promised a 12% raise every year. Then we have two questions. What will her annual salary be in 7 years? And how long will she need to work before she earns an annual salary of $250,000? So first we have to write a function, write the equation. It will be in the form of y equals ab to the power of x. Now the a here is our starting amount, always our starting amount. The b is the growth rate, and x in this case is years. So that's how I fill in the A and the B, and then plug in whatever for X. Y in this problem would be her salary. So I need starting amount, growth rate, and then leave X and Y in there. So starting amount, it tells me her starting salary is 32,000. So I'm going to say Y equals 32,000 times A, or times B, I'm sorry. B is her growth rate. That. Growth rate here is 12%. We looked at what you have to do for a percent. We get a raise here, so we need to add to 100. That gives me 112%. Convert that to a decimal, we get 1.12. So that's the multiplier that you would multiply her old salary with to get her next year's salary, to the power of x. So that is the equation that will give you the graph. Okay, so yes, this equation, I paused during the announcements there. This equation will give you the graph of Selena's salary for every year from here on forever. We want to look at that. We can type in the equation y equals 32,000 times 1.12 to the power of x. And zoom way out. And it curves. Eventually it'll get up in the positives. Way up there. Okay, what I did here, I went and changed some of the window settings so that it looks a little more, I guess we have a nicer view to look at. Our X, our years, I set to go from 0 to 25 years. The Y, which is our salary, from 0 to 500,000, which is $500,000. So that will make the view look a little bit nicer. I kind of had to play around with the numbers to get the nice view, but you can see how it starts way down here at 32,000 and then slowly increases over the next 25 years, I guess. And it will keep going forever. I figured we don't need to look at our salary after 100 years, but 25 gave us a good view. You can do all the same answers without changing that. You can leave the default view and it'll still work just the same. Now back to our questions. What will our annual salary be in 7 years? Remember from earlier, X was years, and the Y is the salary. So when they tell me or ask me what will her annual salary be in 7 years, they're telling me that X equals 7. So we can do two things. I can either plug in 7 for my X and calculate 32,000 times 1.12 to the power of 7, or I can go graph on Desmos, x equals 7, and that should give us a line that intersects our curve. So I'm going to go that way and do it that route. I want to graph another line, y equals 7. So you see Not y. I keep doing y. X equals 7. Sorry. X equals 7. That gives us this blue vertical line. I look right there at that intersection point. In 7 years, her salary is $70,741. Right. So I can come back here and say $70,741. That is her salary in 7 years. How long will she need to work before she earns an annual salary of $250,000? Well, they're telling me her salary needs to be $250,000, so that means Y needs to be $250,000. So what is the X that makes Y $250,000? Desmos is the easiest way to do this. Same concept as we did a while ago. We come to another equation here and graph Y equals 250,000. No comma. I won't graph it, just put a comma in there. Look at the intersection point. In 18.1 years, she will be earning $250,000. So I'm going to say about 18 years. Next question. There we are. The population of largemouth bass in Bailey Lake, not is Bailey Lake, is depleting by 20% every year. Depleting means going down, if you didn't know that. Right now, there are an estimated 3,000 bass in the lake, and then 2 questions. In 10 years, what will the population be? And when will the population reach 5 fish? So, first we need our equation. Again, in the form of AB to the power of X. A is our starting amount. Starting amount is 3,000. So Y equals 3,000 times our growth rate. It's depleting by 20%. So we need to take 100%, subtract the 20, and get 80%, and then convert that into 0.80. That is our growth rate. If they're losing 20%, that means their 80% is remaining in the lake every year. So that's what kind of the number we need to use, what's remaining in the lake. 80% to the power of X. There's our equation. Go graph that on Desmos. Get an idea of what it looks like. So 3,000 times 0.80 to the power of X. Whoa, outside the parentheses. Oh, come on. What is going on here? The power of X. There we go. You can't really see the view there, but if I play with the window, there's the home view. It's there's our little curve. Again, you can get all the answers with leaving the view just like this, but I do want to play with a little bit to make it a nicer view. The X, that is years. I want to start at 0 years, and let's go 50 years. So we'll track it for 50 years maybe. The Y values, the lowest I want to go is 0 fish. The highest I want to go is 3,000 because that's the highest amount. So that's what I'm looking at here. You can tell it drops pretty quickly. So I might have overestimated how far I need to look at the view here. Instead of going up to 50 years, maybe 25 years is good enough. So I think that view there looks to be pretty good. It starts at 3,000 fish and then drops by 20% every year. We got 5 years, it looks like it's down to about 1,000 fish. 10 years, it's about 300 fish, and so on. Keeps going forever and ever until there will eventually be no more. Well, technically 1 fish left, and then once that dies, no more fish. So it's not like our whole wall problem where you walk halfway to the wall. With the wall, you could get halfway there and decimals of the way there. You can't have 0.2 fish left in a lake. So this is a little bit different. In 10 years, what will the fish population be? So population here is y. No, population is y. Yes, so this is x. X is years. The population is y. We don't know what y is, but we know x equals 10. We're trying to find the population. We're trying to find y. We can plug in x, plug in 10 for x, or what I like to do is graph x equals 10. So in 10 years, I see the line, it made this blue line here, the intersection point, 322 fish. Which I brought that up earlier. I didn't even realize what the question was whenever I looked at that number. But about 322 fish. I'm not going to say 0.1 fish, but about 322 fish. When will the fish population reach 5 fish? So again, when, we don't know what the x is. X is the years, but I know the y, the population, is 5. What is x when y is 5? Go back to Desmos. Don't need that. I'm going to graph y equals 5 and see where they intersect. You see that black line that it made down there? It's kind of hard to look at. I'm going to make it orange. All we got to do is find where they intersect. It looks like it might be off the graph here, so zoom around a little bit and right there. Oh, 28.667 years. So at 28 years, there's going to be a little bit above 5. At 29 years, so if we round up, 29 years is the whole number year when we'd reach below 5 fish. So I'm going to say about 29 years. Every single problem on that Snickers worksheet can be worked using those techniques there. Figure out your equation. Sometimes they give you the equation. Graph that in Desmos, and then just plug in either an x or y, whatever they're asking for. Good luck.